Okay, welcome to Day 7, Partial Variation, Unit 2. So we are looking at, can I identify partial variation relationships in graphical, table, descriptions, or in equations? And I know that the initial value of the relationship is the y-intercept if I'm looking at the graph. If I'm looking at the table, when x is equal to 0, that's the initial value, or it's the constant value in the equation, as well as the description having the part without the per. So those are things we're going to be looking for, and we're going to be practicing our work in the textbook on page 212, or in the course notes. There's 2 examples. Or my favorite is on that quiz. So we have 2 that quizzes, Unit 2, lesson check, y-intercept, etc. So we're going to be using MathClips.ca, and you can use MathClips.ca as well if you have a tablet or if you're going to borrow one of my iPads or laptops. If you're going in an iPad, you will need to use Puffin because it needs a special app for enabling Flash. Photon, I think, is also possible. So MathClips.ca, that's where we're going to head in just a moment. We're going to be going to the linear growing patterns clips, and this is what it looks like when you get there. First, though, let's review the difference between direct and partial variation. So on last class, we likely created something very similar to this, where we compared direct and partial variation, and we noticed that both direct and partial variation are linear, but the direct variation has the difference in that it will go through 0, 0. So the direct variation goes through 0, 0. Whoops. So we want to, there we go through the value 0, 0. And that can be noticed then in a direct variation. And if we go to a partial variation, then we notice that the partial variation does not go through 0, 0. We also set up some tables and had noticed that on the table the y value is 0 in a direct variation, but if we have a partial variation, then the y value when x is 0 is something other than 0. Okay, so this is an example of a partial variation. How do I know that? Well, I have this pattern with position 1, position 2, and position 3, and what I'm noticing is that at each position these 2 tiles are repeated, and then what is happening is I seem to be growing by 4 purple stars each time. So I could pretend that the 0th pattern would have, I'd have to go the opposite direction, so I would take away 4 stars this time, and so I would have these 2 green squares or 2 green diamonds left, and that would be it. So for position 0, I would have 2 tiles. So I can recognize that I have something that's sort of always there. So this is my constant, or my always, constant tiles, or always there. And if I look on my table, when I have position number 0, I have a tile number other than 0, and that's how I know that I have a partial variation. So I've just decided to copy the exact same pattern, and I'm thinking if I take this pattern and I don't have these 2 green diamonds, then I will have a direct variation. So I wanted to point that out. So this one is a direct variation because it's growing by the same amount every time, so it's linear, but its position number 0 would have 0 tiles. So that's the difference. So when I go to MathClips.ca, then I selected the linear growing patterns representing section, and I am going to go to the section number 3 called Comparing Families of Line Growing Patterns. You are welcome to work through any part of the clip list that interests you to build your skills. So here we go. This is the exact same pattern that we had looked at before, and so we see that the pattern is represented for a 0 position number, I do in fact have 2 tiles. And now I'm interested in looking at the graph. So the graph, again, we're noticing is linear, so that's not a surprise. But my graph is not going through 0, 0. It's actually going through the point 0, 2, because at position number 0, I have, in fact, 2 tiles. So something else that I could notice is that I could have a pattern rule for this partial variation where I can predict how many tiles I will need based on what number position I'm at, and then I multiply it by 4 because we had noticed that we're always adding 4 for each position we go over. But I also have this additional 2, so I have this constant 2, constant is what's telling me that I have a partial variation. So if I wanted to predict for position number 10 the number of tiles, so predict tiles at position 10, then I can use my pattern rule. So the number of tiles is going to be equal to position number, well that's 10, and then I multiply that by 4 because each time I went over I made 4 more. And then I also have, so that's the 4 purple stars each time, but I also had my 2 green diamonds. So when I work this out, because these are just values, these are all numbers on the right hand side, so I can just use BEDMAS to evaluate. I'm of course going to multiply first, so 10 times 4 is 40, and then I'll add 2, and so I get 42 tiles is how many tiles I should expect in position number 10. And I can use this pattern rule to predict anything, even if I was looking at position number -300 or position number 10,000. So I still have the same pattern. The pattern here, if you're looking at the graph, again starts at 2 and it's going up by 4 because my rate of change is I go up 4 for every one I go over. And I see that the rate of change, the 4, is actually located in front of the x value. So the algebraic representation of the equation, which we'll be working on next time, is just 4 times the x variable, or the independent variable, and then after that I add in that starting value. And that starting value, that's my, also known as an initial value, or a constant. So that was like my 2 diamonds. But at this case, instead of describing patterns with 4 stars and 2 diamonds, I have a story representation. And that is that when I ordered a large chocolate milk, it costs $2 and it costs $4 more for every refill. That's kind of a ripoff, but that makes sense to us. So apparently they want us to buy the chocolate milk, but they're less likely to ask us to refill. Now we did say that we could tell the rate of change. The rate of change is often in the story when you have per, or the word per. We don't have either of those. In this case it says for every. So that is the same as saying per. Okay, so here we have a different pattern, and we can tell from the graph that this is going to be a partial variation. And again, I can tell that it's partial because I see that it's not passing through 0, 0. In this case, it seems like the initial value is 4. So that is, it's starting at 4. So if I was making a pattern, perhaps my pattern number 0 would have 4 things in it. I don't know, 4 stars. And I can tell what my rate of change is, that is how much it's going up by going over 1 and then hitting the graph. And I see that I hit it at 2 more above that, so at 6. So that means that pattern number 1 would have the same 4 stars, but it will have 2 additional things, perhaps 2 circles. And from there on, I will always be changing by 2 because that's my rate of change. So position number 2 will have my 4 stars, but this time it will have 4 dots, 2 from the one before and 2 new ones. Alright, I also have an example here of a story that could explain a partial variation. So we have the Alley Fabrication Corporation creates the most amazing zablobs, so like things. And the warehouse already has 4 things in the warehouse, but the factory is producing or making 2 more each week. So in fact, the graph here could be describing my amount of zablobs in the warehouse. So this is number of zazblobs in the warehouse, and this is the week number. So we can see that as the weeks increase, then I have more and more zablobs. I'm also going to go back to the representation on the other page and see what else I could do with that. So we see that we have the same representation. We have the algebraic equation, and again I'm starting at 4 thingies or zablobs, and I'm adding 2 of those each week. So that's one thing that I could do to represent it. And of course this is the most concise way because we have much less writing. So I've just asked the clips to show me, instead of the equation and the story representation, I've asked it to show me in a pattern. So we've already made a pattern, but this is a different version of the same pattern. So we have that pattern, and again we see the same graph. Lastly, I'm just going to check and see what happens if I change the 2 or the 4. So the 4, again, was coming from the y-intercept, or the initial value. So if I change the 4 to a smaller number, like 3, then I watched my graph here go down from 4 to 3. But I also noticed that these 3 initial circles that are always there, they have changed from being 4 to 3. So I wonder what will happen if I change the 2 to the value 1. So again, looking at my pattern, I'm going up by 2 every time, so I'm guessing that that will change. Instead of 2 triangles each time, I will add 1 triangle. And I also see that my graph is starting at 3 and goes to 5 and 7, etc. So I'm thinking if I change the 2 to a number 1, then I would, instead of going up by 2 or having a rate of change of 2, I'm thinking it'll have a rate of change of 1. So let's see what happens. And I was right about the triangles, and if I look here, I've gone from 3 to 4, and I've gone from 4 to 5 as I move over 1 each time, so it looks like that does in fact change my rate of change. So with these ideas, you're going to be doing pictorial representations, graphs, and solving problems about making predictions with partial variation.